Welcome back to the Build Your Own PokerBot series. In this video we will be focusing on reducing the size of our game tree. So Limit Heads Up Texas Hold'em has about 10 to the 13 game states, which isn't so bad considering it's about the same size as checkers. But when we get to No Limit Texas Hold'em, we have about 10 to the 161 states, which is about 2 times the number of atoms in the universe. So in both cases, reducing the number of game states is necessary in order to hit Nash equilibrium at a reasonable amount of time. And remember, the CFR algorithm we are using requires more iterations than other algorithms, such as Monte Carlo tree search. So this really compounds the need to reduce the size of our game tree. So there are 2 major ways we can reduce the size of our game tree. The first one is hard coding. And this is us basically changing the rules of poker to help our bot. First example of this would be no quad betting. So that is player 1 bets, player 2 bets, player 3 bets. That's a triple bet, and then one more will be a quad bet. Now this rarely happens in real play, so we can just avoid this altogether and not optimize it. So if an opponent triple bets, the bot will be given 2 options to either call or fold. The other thing we can do is hard code strategies. So it's actually possible to code strategies of every pre-flop hand, and people have actually done this. Or we can do a simple thing like always fold 2-7 offsuit, the worst hand in poker. Or we can take the option to fold pocket aces or something like that. One last note about hard coding: it should be used in practice, not in research. It's very easy to dismiss results in research if you use these kind of hard coding strategies. So the second way we can reduce the size of our game tree, and what we'll be focusing on for the rest of this video, is abstraction. And abstraction means we group similar parts of the game together. In doing this, we can reduce the amount of our game states quite considerably. So No Limit Texas Hold'em can actually be reduced to about 10 to the 12 information sets, which again is similar to the size of checkers. In a extreme example with a coarse abstraction, we can reduce it to as little as 1.2 million information sets. Now there are 2 types of abstraction that we're going to be using: action abstraction and information abstraction. Now, for the context of poker, we'll be calling information abstractions just simply card abstractions. Okay, so action abstraction. So No Limit Hold'em has about 20,000 actions at each level. And this includes every single bet size. So you could bet $1, $2, $3, all the way up to 20,000, which is ridiculous. So the simple solution is to separate bet sizes into separate buckets. So 0 to 100 is a bet, 100 to 200 bet, and so on. And anytime, if you're playing a human and say they bet 99, well, that would just round it to the buckets it's in. Now we don't have to choose between 0 and 100. We can choose how small or large these buckets are. Now if we go too fine or too close together, it's going to be expensive. It's going to take a long time to converge. And if we go too coarse, the bot becomes exploitable. Humans can bet right in the middle, and the bot may not know what the bet size is or what the pot size is. The real one is. So action sizes can be determined by several different ways. The first one we already lightly discussed, which is using a uniform strategy, which is again bucketing into ranges. It could be 100, 200, 300, or maybe 1% of the stack, or 1% of the pot, 2% of the pot, etc. Another thing we can do is we can parse real poker data played by humans and estimate maybe the top 3 most common bet sizes that are used. And the last thing we can use is something called parameter optimization to help us find the ideal bet size. And it'll look something like fold, call, raise a certain amount, or go all in. And the X, or the raise amount, is determined by using gradient descent. Okay, now moving on to card abstraction, let's start with the pre-flop. So pre-flop, there are about 1,300 different possible combinations of our 2 pocket cards, and 169 with some very simple abstraction. So This is just suited cards are placed in one group and off-suited cards are placed in another. So king of clubs, 10 of clubs will be the same as king of diamonds, 10 of diamonds. So they'll just be king 10 suited. So that's a very simple abstraction, but we can go one step further by bucketing similar hands together. So this will be something like if we have pocket 8s, we're going to put them in the same group as pocket 9s and pocket 7s. So kind of mid-level pairs we're going to put the same way. So just a quick note, we want to bucket similar hands together, not similar strength hands together. So there's something called the Sklansky method or something like that, where if you have a hand like Jack 10 suited, you're going to play the exact same as like pocket 8s. You want to avoid doing this with our bot because it can actually give us worse results. So again, we're bucketing similar hands together, not similar strength hands. And bucketing preflops, we can actually go as little as 5 buckets and still hit a good Nash equilibrium, but 10 to 15 is better. Okay, next we're moving on to abstracting the flop. And the key thing we're going to do with the flop is we're going to ignore the suit of the card whenever possible. So if there's 2 or more of a suit on the flop, then it's considered suited, otherwise it's off suited. So example, say we have king 10 3 rainbow, so all 3 of the cards are different suit. We just simply convert it to king offsuit, 10 offsuit, 3 offsuit. But if we have 2 or more of the same suit, so in the second example, king of clubs, 10 of clubs, 3 diamonds, we then convert the similar suited hands together. So king of suited, 10 suited, 3 offsuited. The bots I make, I don't play for gut shot flush draws. So say I have a king of diamonds, 10 of diamonds, and there's 1 diamond on the flop. I don't play for the flush, but you can obviously add that if you wish. Another optional thing we can do with the flop is use rank abstraction. So if we have an unpaired low card, for example, so 5 and under, it's not paired or anything with our cards, we just simply turn this into an L for low card. So we're going to skip the turn for now, and we're going to go right into how we abstract the river. So on the river, there are actually about 2.4 billion combinations of hands. And what we want to do is reduce that number using automated abstraction. And how this is going to work, we take every possible hand on the river, and we run simulations on that in order to calculate a winning percentage. So each simulation is going to give 1 point for a win, 0 for a draw, -1 for a loss. And the idea behind that is that similar hands will give a similar score. So a 10 high straight will probably win the same amount of hands as maybe a 9 high straight or something like that. So once we have the score, what we're going to do is put every hand into a class using a clustering algorithm. In this case, K means clustering. And we get to choose how many classes we want to cluster into. So on the high end, for fine abstraction, we go to 1.25 million buckets. And for the extreme example on the other side, we can go as little as 200 classes. Okay, now we're going to get how we're going to abstract the turn. So on the turn, there are about 55 million different combinations. And again, we're going to reduce this with automated abstraction. So just like before, we're going to run simulation on every hand to calculate the value of that hand. But this time we're going to use a bot or a pre-computed strategy to play the game. And we're going to do this because it takes into account actual game strategies that we're going to use, like bluffing. So an example, say player 1 has maybe a pair of 2s, player 2 has maybe a straight or a flush draw. Well, player 2 can actually have the better hand by using semi-bluffing or getting lucky. So this is kind of like a chicken and the egg problem. We need a bot to make a bot, but the bot we need doesn't actually need to be that powerful. It just needs to give rough, good strategies of how you should play on the turn. And again, just like on the river, we're going to cluster all these games using K means neighbor, and we get to choose how many classes we want. So for a finer abstraction, we can go to about 2.5 million buckets, and on the extreme low, we can go as little as 900 buckets. So that's all we're going to cover right now on abstraction. Let's just quickly jump into a quick code. Okay, so real quickly how we go over abstraction. Let's start with the preflop. We get a function, we send in 2 cards, and we're going to grab the suit from each of them and the rank for each of them. Now to determine if they're suited, we just check if suit 1 equals suit 2. Then we calculate the rank difference. So this is rank 1 minus rank 2. And if we want to know if they're paired, well, rank difference would be 0. If they're connectors, rank difference would be 1, and so on. And we take this information and then we're just going to throw it in buckets. So here we have, let's go suited connectors. The rank difference will be 1, and suited will be true. And then we can bucket each of them into 3 categories, high, middle, or low. And we do that for as many as we want, or however precise we want. Okay, moving on to the flop. First thing we do is we run through the 3 community cards, and we're going to run a counter, check how many suits are in total. And if there's 2 or more, every one of that suit, we're going to put an S after it. If not, we're just going to make the suit off-suited or an O. We do that for the pocket cards as well as the 3 community cards. Okay, now on to the simulations. We're going to use this estimated win rate thing, and we're going to take in the pocket cards and the 5 community cards. First thing we do is we combine them all into one 7 card array, and then we're going to look for the best 5 card hand we can make out of those 7 cards, and that's what we're going to run in our Monte Carlo simulations. And so to do this, we just pick 2 random cards for our opponent. We do the same thing. We try and find the best 5 card hand they can make out of the 7 cards. And then we evaluate them and then compare them. So a winner gets a score of 1, -1 for a loss, and 0 for a score or tie. And then we just throw this into a K-means clustering algorithm. So if we take this abstraction that we have and run it in our CFR algorithm to get a blueprint, we'll get a pretty good bot. It'll be able to beat probably top amateur players or semi-professionals in a small sample size. But if we really want to get a top-tier poker bot, we're going to have to reduce the exploitability. And we'll be covering that in our next and final video.